Hi, this is Professor Dorr, and this is lecture number 16 of EE310, entitled Introduction to Frequency Response. In this lecture, I'm going to introduce frequency response. I'll start off using an intuitive example scenario. We're actually going to talk about an airplane flying over San Diego, trying to listen to a navigation station coming from LA Airport. You may have remembered a similar example in the very first lecture when I was selling EE310 to you. But we're going to go through that example to just give us a flavor of why we do frequency response. And then what I'm going to do is I'm going to compare frequency response to the time domain stuff we've been doing. In EE310, you're getting information pumped out of a fire hose. And I want to make sure that you can keep all the time domain thuds and boings stuff and the frequency domain stuff kind of in the right compartments in your head. So I'll spend just a little bit of time going over that. I'm going to introduce one of the most valuable tools that I know for frequency response. It's called Asymptotic Analysis. And what it allows you to do is quickly get the magnitude of the frequency response at DC and then at infinite Hertz. So you can get the DC response and then the response at infinity. And you can do it really easily for the circuit, no matter how complicated the circuit it is, well, to some degree. But then you can also do it for the transfer function. So you have these two data points, one at DC, one at infinity, and you've got it for the transfer function and for the circuit. And if they agree, then you're probably doing something right. You get a warm and fuzzy feeling. If they disagree, you're in trouble and you've made a mistake. So it's a really, really valuable tool, both for the class, but also when you're out working in industry and people are flopping circuits up on the projector or the whiteboard in meetings or whatever. It allows you to quickly analyze them. So I'm going to give you an example of using a transfer function for frequency response. We're going to do a lot more of those later, but we're going to walk before we run and do one that's nice and straightforward. And of course, we'll do asymptotic analysis of it also. And then finally, I'm going to give you a Matlab script that you can use for computing frequency response. Matlab has a nice function called Bodhi that you can use for frequency response. The one that I wrote a few years ago is a little bit more tailored to this class. So you might find it a little bit easier to use, and also you can modify it and control it. And I hope that you'll use my little compute frequency response function for the homework problems to check yourself, and then get so good at it that you can use it to check your work on the quizzes. Note I said check the work, not do the work. So let's get started with the lecture. So as an introduction to frequency response, like why do we need it? Let's look at an example of an airplane. Believe it or not, this is a picture of an airplane. And it's flying at about 10,000 feet coming from Mexico City. And it's going to land at LA Airport. And it's listening to a navigation signal coming off the tower at LA Airport. It would be a VOR signal. And in reality, if it's going over San Diego, it might be listening to a VOR station that's a little closer. But for my example, let's say it's coming right off the tower at LA Airport. This is probably the worst drawing of the control tower at LA Airport that you will ever see, but it's actually about the best that I can do because I'm not a very good drawer. And so the airplane is listening to this station that's only 30 watts of transmit power, and it's 100 miles away from the airplane. Now, the airplane is flying over a strong FM radio tower. In this case, it's KGB 101.5, and it's spitting out about 500 watts. And look at the airplane. it's only 2 miles away from KGB's tower, and it's getting blasted with 500 watts of power. And the frequencies of these two signals are pretty close together. The desired signal, the signal that the airplane wants to listen to and provide safety for all those passengers, is at 108 megahertz, and KGB is at 101.5 megahertz, because the FM band is 88 to 108 megahertz, and the aircraft navigation band for VOR and localizer is from 108 to 118. And just to continue things, 118 to 136 megahertz is the aircraft communication band. But they put the aircraft navigation band pretty close to the FM commercial radio band. So this poor little airplane is trying to listen to 30 watts at 100 miles away, and it's stuck with 500 watts at 2 miles away. Think about if you're a party and you're trying to listen to someone with a fairly soft voice, and that person may be, in a conversation that's going on next to you, and then you have some big loud person drunk with a really loud voice, and it's really hard to understand the person you want to listen to. So the airplane kind of has a similar problem. Now, I have to digress a little bit, because why does KGB get to spit out 500 watts, where this little navigation signal that people's lives depend on is only 30 watts? Why would the FCC allow that? And there's a good reason for that. It's because you always have line of sight communication between the airplane and the control tower. If you don't have line of sight communication, that airplane's kind of in trouble. And in the case of KGB, they want to be able to put out a signal that you can hear all the way from San Diego up to Fallbrook or Temecula, because the wider their coverage area, the more advertising they can sell and the more money they can get for it. And they know that cars are going to go down through valleys and under bridges and stuff like that. So they need a really powerful signal so that the signal doesn't go away when people are driving. But apparently this frequency response stuff that I'm going to show you is pretty useful, because this is a completely viable and safe scenario. So that's why KGB gets to output 500 watts and air traffic control gets to output 30 watts. So let's look at the scenario like engineers. We're going to look at this from the perspective of the airplane. And I'm going to show you a new instrument, which you can go out into the lab and find one of these. It's called a spectrum analyzer. And where an oscilloscope shows waveforms as a function of time, the spectrum analyzer shows signal power as a function of frequency. You see that? An oscilloscope is a time domain instrument. The spectrum analyzer is a frequency domain instrument. And we don't have them in the EE310 lab at San Diego State, but we have them in our RF labs. And it's a very common piece of radio frequency test equipment. So what the spectrum analyzer displays is what is there. And so I'm going to connect the spectrum analyzer up in the airplane. I'm going to put it in the back seat and somehow plug it in and connect it to the antenna connector on the airplane. And here's what I'm going to see. At 101.5 megahertz, I'm going to see a big old spike, and that is KGB. Now, it's actually about 100 kilohertz wide, because that's the information that's modulated on it. But when I'm looking at this kind of resolution, it kind of just looks like a little line. And so that's what I see at 101.5 megahertz. And then I see a little tiny spike down here that represents my signal coming from the LA tower. And if we work out the math, we are getting at the airplane 1 milliwatt from KGB. That's a milliwatt into a little bitty antenna. That signal's going out all over the place, but we're capturing a milliwatt in an antenna about that high, which is really pretty cool. But our signal that we want to listen to is only a picowatt. So you might be thinking, hey, professor, you can't show that this way on your graph, because if you're showing a milliwatt here, I'm not even going to see a picowatt. And I'm going to say, hold that thought, because we're going to get to that in a little bit. And we're going to get to it by talking about how much money the Koch brothers have, how much money Kim Kardashian has, and how much money I have, and how much money you have. And that's how we're going to explain it. So right now, just take my word for it that the spectrum analyzer can do that. So the spectrum analyzer shows what we have. It shows what's coming in. What is this composite signal? Now, the aircraft antenna is a little bit frequency selective, but if I really looked here on the spectrum analyzer, I'd see other cool stuff. I'd see the business band at like 140 megahertz. I'd see the 2-meter ham radio band at 144 to 188. Sorry, 144 to 188 megahertz. I'd see all kinds of cool stuff going on. And if you ever get your hands on the spectrum analyzer, just stick a little antenna up in the air and you'll see all kinds of neat stuff going on. But in this example, I'm just showing the two things we care about. 1 billion times more power, that poor little aircraft receiver. So here's what we're going to do. Here's a drawing of what's going on in the airplane. I've got its antenna. This is kind of the symbol for an antenna. And then I've got a filter, which is kind of a mishmash of linear components. It's got resistors, it's got capacitors and inductors, transformers. We try not to put resistors in it because resistors just dissipate and waste power, but I drew one in here anyway. So this circuit is called a filter. And you're going to see that it is the thing that rejects the signals we don't want, but passes the signals we do want. Now, after the filter, we're going to go into the demodulator of the radio, and the demodulator is the thing that converts this coded signal from the navigation station to the display that the pilot sees. And you notice this is probably the worst picture of a display that you've ever seen, but 3 things I avoid in my life. One is boats, one is opera, and the other is airplanes. Because if I ever started to get interested in any of those, that's all I would ever do. And I got all the distractions that I need. So I'm quite happy not really knowing what a VOR display looks like, even though I've designed a few radio receivers for aircraft. Back to the example. So here's our signal path. And what I'm going to show you first is what the spectrum analyzer displays at each point. Remember, the spectrum analyzer tells us what is there. It's a measuring instrument for telling us what is coming in the input. And that's going to be important in a second because we're going to look at another kind of display. And I want to make sure you understand the spectrum analyzer display. It just tells us what's there. So let's look at what comes out of the antenna on the airplane. Or in other words, we're looking right up here at what we see. So what I see is this composite signal, and I see oodles of KGB, and I see a little tiny VOR signal. Now what I'm going to do is go through my filter. So I'm going to run my signal through the filter, and I'm going to show you a different plot. This plot is also a frequency domain plot, just like the spectrum analyzer, but what it's showing is the response of this filter at each frequency. So for this particular filter, if the frequency is 101 megahertz, man, you get no response, right, or hardly any. But if the frequency is 108 megahertz, this filter says, come on through, and lets it right through. So this is an actual plot of the frequency response of the filter, where the spectrum analyzer is showing you what is there when I look at a signal. Make sure you can keep those straight, especially when you have a job interview. If you go to a job interview and you see a spectrum analyzer and you can just tell the difference between that and an oscilloscope, you got the job. All right. So here's the frequency response of our filter. So it looks like 101 didn't get through, 108 did. So now let's look at our filtered signal. Let's look at the output of this filter. And look at this. I'm looking at the spectrum analyzer again, or in other words, I moved the input cable of the spectrum analyzer from the antenna over to the filter output. And check it out. I don't see very much KGB. It's pretty much gone, but my VOR signal, my navigation signal, went right through. So what the filter has done is it has filtered the undesired signal from my composite response. So the filter eliminates the interferer. And one more time, because this is so important, the spectrum analyzer displays show what is there. The network analyzer displays, and we have network analyzers too, and they're really cool and they're fun to use. The network analyzer shows what the filter does. And this plot that comes out of the network analyzer shows the frequency response of the filter, and that's what we're going to talk about in this unit. So let's actually look at a frequency response plot. Here's one right here. And you notice that I wrote signal amplitude here, which really kind of resembles the spectrum analyzer display. But I want you to think of this as the network analyzer display here. So it's showing the frequency response of a filter. So it looks like low frequencies get through just fine, and then when the frequency gets a little high, the filter starts not passing as much. The amplitude is going to go down, and then at high frequencies, nothing's going to get through. So what kind of filter is this? This is a low-pass filter. In other words, low pass, low frequencies pass. Say this was an audio filter, for example. Then most of the intelligence in voice really is, voice does not have a lot of intelligence above about 4 kilohertz. The energy in our voice is at a lower frequency, but the intelligence in our voice, meaning the articulation between the S's and F's and stuff like that, that's more around 4 kilohertz. So what if there was an annoying tone accompanying my voice at 10 kilohertz? Say I was trying to talk and you'd hear this. If that was 10 kilohertz, you had this really irritating tone. Then you could put my voice through this filter and you'd get the energy in my voice here, you'd get the intelligence in my voice here, but that 10 kilohertz tone would be gone. And so it'd be easier to understand my voice. So this is a low-pass filter. Let's look at how we might generate this plot. And we're going to do it with the stuff that we have in our 430 labs. A signal generator. This is an AC signal generator. Here's the circuit that I want to test. This is the gizmo that's given us this frequency response. And we're going to go into an oscilloscope. And here are the rules. I'm going to keep my AC input level constant. So let's say that the input level is going to be 1 volt peak or whatever, but it's going to stay constant with frequency. And then I'm going to measure the amplitude with the oscilloscope. So I'm just going to look at, the peak-to-peak value or the RMS value or something like that. But I'm going to vary the frequency. And what's going to happen? The impedance of all these inductors and capacitors and stuff, it's going to change with frequency, right? The inductors are going to be doing the J omega L thing. The capacitors are going to be doing the 1 over J omega C. And so those impedances are going to change with frequency. So what do you expect? As I change the frequency of the signal going into that filter, what comes out of that filter, its amplitude and its phase, is going to change with frequency. So let's take this filter, for example. We put in 100 Hertz, and we see a nice big old signal here. And then I turn up the frequency of the signal generator, and the signal level on the scope gets smaller and smaller and smaller. And finally, when I'm really high, even though I'm putting in a signal here, I don't see any signal out here, high frequency. So that's just a simple way to measure frequency response. As usual, our textbook, Alexander and Sdsu, says it beautifully. The transfer function h of omega of a circuit is the frequency-dependent ratio of a phasor output, y of omega, which is an element voltage or current, which means you can basically look anywhere in the circuit, to a phasor input, x of omega, which could be a source voltage or current. So the transfer function is the frequency-dependent ratio of the output to the input. Now, in the last couple of chapters, you've been determining transfer functions, but we just gave you one frequency. We gave you the inductor and capacitor values and said, oh, by the way, the frequency is 1,000 Hertz or something like that. Or to simplify the problem, sometimes we didn't even tell you the frequency, and we just said, hey, the impedance of this inductor at the frequency of interest is J50, or the capacitor is minus J275. So you've been working with transfer functions, but now you're going to calculate transfer functions, then we're going to change the frequency and look at how the transfer function changes. Here's kind of a picture of it. We've got an input voltage. This is a picture of this statement. And it's got some input amplitude at a angle of phi. And we have a transfer function. And it is going to have an angle of delta, and then we've got our V out. And V out over V in is equal to H, so V out is equal to V in times H. And the magnitude is going to be the magnitude of V in times the magnitude of H. Give this guy some absolute value symbols here. And the phase is phi plus delta. So here I showed the transfer function as a constant, meaning that that is at a single frequency. But what we're going to do is we're going to change the frequency. Now, before we go on with this, I want to go back and connect this to our thuds and boings, because you're getting a lot of information in this class, and I want you to compartmentalize everything in the right place. So thuds and boings were transient response. They were what happened when we had a circuit that had been sitting one way a long time, and then we whacked it with something and it went boing, or it went thump, or something like that. And then it ended up in another steady state. And we looked at that in the time domain. And we got functions like this. Response of t is equal to a e to the minus alpha plus j omega t. Looks like we got a boinging circuit here. And we could expand that, or we could simplify it, however you want to look at it. But for sinusoidal steady state, we're going to set alpha equal to 0. And the basic idea is that any transient in the circuit has died. So I've got my circuit and I turn the input on and it goes and we end up with just a sine wave, right? Here it is, circuit's quiet, we're going to turn on a switch and we're going to sing the response. Quiet. And the is the sine wave that we're talking about when we do both AC steady state analysis and frequency analysis. So for sinusoidal steady state, our response is going to be a e to the j omega t. Alpha is 0, so e to the 0, that's 1. And more, you're going to see me use j omega. I'm going to use S instead of j omega. I said goodbye j omega, it's S now, but in reality, I still go back and call it j omega. But the reason that I'm pushing the S on you is, one, because it's less characters. And in Matlab, of course, you say S equals 1j 2 pi times the frequency, and then you use S everywhere else in your script. You'll see that in a bit. But also, S is our Laplace transform variable. And you're going to see that when we get into Laplace transforms, because in Laplace transforms, we can handle both the transient and the steady state. All this stuff is a subset of what we can do with Laplace transforms. But steady state is very convenient to do with phasors. So that's the way we do it. But the relationships between Laplace transforms are there. And this S is the same S that we're going to use in Laplace transforms. Let's do a simple example. Find the transfer function and the frequency of the RC circuit, shown right here. So before I solve the right problem, find the transfer function and frequency response, i.e. frequency domain stuff, let's solve the wrong problem. The wrong problem is I put a unit step into this circuit, and I want to know the output as a function of t. So what's wrong is I'm doing a time domain, not a frequency domain analysis of this. So if I put a step into this circuit, we go right back to our rules and we say we can't change the voltage across the capacitor quickly. So at t equals 0 plus, obviously the voltage will be 0. And at t equals infinity, another steady state condition, we're going to have no current through the capacitor. So that means KVL on the fly says this voltage and this voltage will be exactly the same because there's no voltage drop here. So I'm going to start off at 0 and I'm going to end up at 1. Now, what do we have in here? We have an exponential. And you learned that in EE310. But of course, if you buy this fine book right here, it will show you how to calculate that equation for any first order circuit, given a set of initial and final conditions. So I hope that you buy this book because it is going to help you. And especially if you're at Sdsu, bring it to me, let me sign it. I'll give you a $5 kickback because I just want you to have it. All right, now let's solve the right problem. And so the right problem is find the transfer function and the frequency response of the circuit. Think frequency domain. Transfer function's pretty easy. We've been doing that for a while now. V out over V in, we're just going to use a voltage divider. The impedance of the capacitor is 1 over Sc, and of course the impedance of the resistor is R, so the voltage divider, V out over V in, is just going to be 1 over Sc divided by R plus 1 over Sc. We're going to multiply top and bottom by Sc, and we get 1 over 1 plus SCR. At this point, I want to introduce the tool asymptotic analysis. This is one of the most useful things I ever learned. It's not really covered in our book, but it's absolutely covered in my class. And we're going to use it for our homework. We're going to use it like crazy in our lectures. We're going to use it on the quizzes. And you guys and ladies are going to use it in industry. Then you're going to thank me for it. And you're going to come back to my office at Sdsu. And you're going to buy me a yummy cup of Starbucks coffee so I don't have to drink that crap that I stock in my office. So asymptotic analysis is really good for you, and it's really good for me because I like this coffee a lot better than that Keurig crap that I pour in my office. So here's the deal. At the highest level, what asymptotic analysis is going to do is it's going to allow you to look at a circuit and say, what's the frequency response at DC? And then what's the frequency response at infinity? Response at DC, response at infinity. Then you're going to look at the transfer function you derived, which hopefully represents the circuit, but you might have made an error. And you're going to do the exact same thing. What's the response at DC? What's the response at infinite frequency? If those two things agree, you have a nice warm and fuzzy about your solution, though you're not guaranteed it's right. If they disagree, you are guaranteed that it is wrong. So what I have done with this throughout my career, remember I worked 35 years in industry before coming and pretending like I'm a college professor, is people would flop a circuit up in a meeting or a design review or something like that. And they would say, okay, here's my circuit, it does this. And I would quickly do some asymptotic analysis. And every once in a while I'd say, that circuit doesn't do that. So, well, I got all this mathematics and analysis and simulation that says it does. Say, that circuit does not do that. Or there were times when I would say, hey, your transfer function, I can tell you that's not what your circuit is doing. And when someone can poke a hole in something like that, you got to do it tactfully, and you got to do it nicely, and you got to do it with respect for everybody in the room. But you save everybody a hell of a lot of time when you can find problems. A lot of your engineering career will be spent on things that go wrong, not that things go right. I'm digressing, but when things go right, you ship the thing and you start selling it. When things go wrong, that's when you, as the engineer, as the specialist, get to play with it. So if you can solve problems quickly, you're worth a lot more to the company. And if you can identify problems before other people identify them, you're gold. And asymptotic analysis is really going to help you do that. So let's look at how to do it. I've got a circuit here, and we just derived the transfer function for it. We believe that it is 1 over 1 plus SCR. Let's look at the circuit. At DC, I'm going to go right back to the rules. I know that I have no current through that capacitor at steady state. I'm sorry. That's right. I have no current through that capacitor when the frequency is 0. Because doesn't DC just mean steady state? So I have no current here. So if I have no current here, I have no voltage drop across the resistor. So this voltage is equal to this voltage. V out equals V in. Response is unity. It's 1. Now let's go down to here. So response at DC, well, S is equal to j omega. Omega is 0 because the frequency is 0, so let's put a 0 here. 1 over 1, that's 1. What did we get when we looked here? 1. Now let's set the frequency to infinity. And now, instead of using our rules from chapter 8, let's just use the formula for the impedance of a capacitor. The impedance of the capacitor is 1 over j omega c. And omega is infinity. So I have an infinity in my denominator for 1 over j omega c. So 1 over infinity is 0. So the impedance of my capacitor at infinite frequency is 0. So what's my voltage divider going to give us? 0 over 0 plus R. Or in other words, if I have a short circuit here, or an impedance of 0, I'm not going to get any voltage. So I'm going to say the response is going to be 0 at infinite Hertz. And now let's look at our transfer function. Let's put an infinity here. 1 over infinity looks like 0 to me. I'm going to talk a lot about asymptotic analysis, and I'm going to use it a lot because I just use it in my work all the time. But it is nothing more than page 6 of this lecture. It's nothing more than what I did. We're looking at DC, we're looking at infinity. Let's do it again, just because it's so much fun. So now we have a resistor and an inductor. Let's get a transfer function. Pretty easy, just a voltage divider. V out is equal to SL divided by R plus SL. I think that's the transfer function. So let's see. Let's go to DC. We'll go back to the rule. And the rule that we're using for our asymptotic analysis, or the two rules we're going to use, is that at steady state, we have no current through the capacitor. We just use that one, but we have no voltage across the inductor. So at DC, I'm going to say V out over V in is going to be 0 because I got no voltage right here. Let's put 0 into our transfer function. 0 divided by 0 plus something is going to give us 0. So hey, they agree. Now let's go to infinite Hertz. Now we're going to use the formula for the impedance of an inductor, which is j omega L, and omega is infinity. So the impedance of this inductor is now infinite. It's like an open circuit, right? It's like it's not even there. So that means I'm going to get no current flow through here. So that means I have no current through the resistor. I have no voltage drop. So the frequency response is going to be 1 because V out over V in is going to be 1. Now let's look at the transfer function. This R becomes insignificant, and I have infinity L divided by infinity L. Nobody tell the mathematicians, but we're going to call that 1. So again, we've gone through and we've got a nice warm and fuzzy that our transfer function does indeed match our circuit. Now what I'd like to do is I'd like to address the issue that we had at the beginning of the lecture here. I had a milliwatt and a picowatt, and I put those rascals on the same graph because, and obviously I didn't use linear scaling because if I can see a milliwatt, I'm sure as hell not going to see a picowatt down here, right? But I can see a picowatt. What's my trick? So what we're going to introduce is decibels. Decibels, where do they get a goofy name like that? Well, Bell, if we put a capital on it, would be Alexander Graham Bell. And that's where we get the concept of bells. And we define 10 times the number of bell. That means 10 times, and we call it decibels. And we shorten that down to dB. And let's define it. Gain expressed in number of decibels is 10 times, that's the deci, the log of P2 over P1, meaning the power in one place divided by the power in another. Typically, the power output of a filter divided by the power input. So the bell gain is log of P2 over P1. Decibels is 10 times that log. That's our decim. So this is the basic definition for decibel right here. And it's a power ratio. But if the resistance is the same on both sides of our network, or in other words, R is the same, what I'm going to do is I'm going to say, well, really, I can say the same thing by saying the gain in decibels is 10 times the log of V squared over R, V2 squared over R, divided by V1 squared over R, and the R's cancel. And what you see is that I end up with a square in my numerator, the R's cancel, and I end up with 20 times the log V2 over V1. And so this is the definition of the decibel gain for voltages. But the real definition is here. It's the power. But when we talk about voltage gain, we're implicitly saying that the resistance is the same on both sides. Now, engineers just screw this up horribly. Engineers, when I do job interviews and I interview people, engineers, even if they work with dB all the time, they often mess this up. I ask them, give me the definition of decibels, and they give me the 20 log, and then I ask them where that comes from, and they always mess up the 20 versus the 10. So if you understand this well, and all you have to understand, it's as simple as right here, what I want you to do is bet your coworkers lunch on decibels. I have got more good lunches out of making bets on dB, because engineers think they understand it, but it's really just a buzzword for a lot of them. If you really understand it, you'll trip them up. Always be respectful, be kind, but get those free lunches. So why do we need another term? And what I want to do is I want to give you a quick sales pitch on dB. Obviously, the first sales pitch is that I can show a milliwatt and a picowatt on the same graph. And that's really the sales pitch I'm about to show you. But let's have a little fun with it. Let's look at who has the money. And let's start with the Koch brothers. I think one of them is dead, so there's only one of them now. But they're worth actually a lot more than this, because this slide is a couple of years old. So the Koch brothers are worth about 110 billion. Zuckerberg, the Facebook guy, he's at about 45 billion. So I can definitely see that the Koch brothers have about twice as much money as Zuckerberg. Let's see, George Clooney, he's got some money, right? He's an actor. Yonder Alonso used to play for the Padres, but he was just beginning in his career, so he didn't make that much. Made about $1 million. Phil Rivers, the quarterback, well, the former quarterback for the Chargers, the one who's turning me into an Indianapolis fan, he was making around 12 million, or his net worth was around 12 million. And you can't forget Kim Kardashian. She's actually worth more than Phil Rivers. Go figure, but you know, she's around $20–30 million. And then of course there's Professor Dorr. It's kind of hard to see where I am down here, but hey, at least I'm doing better than you guys are because you're all in debt. So the problem with my graph here is that I can kind of deal with the Koch brothers and Zuckerberg, but it's important to know whether Kim Kardashian is making more money than Phil Rivers. I need to know that. So my graph here is just not doing it for me. So I need a better graph. So what I'm going to do is I'm going to plot the log of how much these folks are making. So now instead of a linear plot where we have a certain number of dollars for each increment, what's incrementing linearly is the exponent. So here's 10 to the 4th dollars. Here's 10 to the 5th dollars, 10 to the 6th dollars. Sorry guys, but I can't represent your negative worth on this graph, but after you graduate, you're going to be up here big time. But the exponent's going up linearly. 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, 10 to the 8th, blah, 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 all the way up here. So I look at this plot and I go, ooh, I like this. I can kind of see that Phil Rivers, yeah, he's making 20 or 30 million dollars. Or it has 10, 20 or 30 million. Kim Kardashian, she's up there around 80 million, but I can definitely see she's doing better than Phil is. And George Clooney, you know, he's kind of been at it a while. So he's got more money than both of them, but I can really see that. Now, Clooney has, what, 100 and maybe $200 million? Do I care if somebody gives Clooney $1 million raise? Knowing Clooney, you'd probably give it to charity, so you got to let him for that. But I really can't tell whether he has 120 or 100 and however. I certainly can't tell his net worth down to the million. But for Yonder Alonso, I know he's not $2 million. He is $1 million. But, you know, for Yonder Alonso, 100K is important to old Yonder. Clooney couldn't care less about 100K, and the Koch brothers wouldn't even sneeze for 100K. But my graph is showing me what's important because it is logarithmic. So let's say that when I had my company, I came home and said, I got a $1 an hour raise. And one of you who's working at Starbucks or something like that comes back and got a $1 an hour raise. Who's happier? You're happier because your raise was about 10%, right? For me, it was, when I had the company, it was a lot lower than that. So what would make us both happy at the dinner table that night is you got a 10% raise and I got a 10% raise. And that is what would show up on this curve because 10% on this curve is a finite increment. If Alonso gets a 10% raise, he's here. If Clooney gets a 10% raise, he shifts by the same amount. So you remember the power ratio of 10 to the 9th at the beginning of the lecture? Remember that? Well, there's your milliwatt, there's your picowatt. The spectrum analyzer is calibrated in dB. It's plotting the log, and this is why it does it. So the spectrum analyzer can show the Koch brothers' money and Alonso's money, even my money, on one screen, and you can see them together. That's the value. While we're at it, What other things work in dB? Oh, how about our hearing? Our range of hearing, we can hear really, really quiet things to really, really loud things. So when we do hearing tests, if you ever go get a hearing test, you're too young for those, but I'm not, and I've played too much music. So I get hearing tests every once in a while. They always present the information in dB. When we talk about how bad an earthquake is, we put it on the Richter scale because a constant amount on the Richter scale really gives us an idea of the incremental damage and loss of life. That's why we put earthquakes, we measure them logarithmically on the Richter scale. Kind of a cool little example of it is how the kitty cat can see at night. At night, Bella, she can jump up on the dresser. She can do all this stuff when the lights are off and I'm trying to sleep. But she can also see in the bright sun. That's why her eyes, they don't go like this like our eyes do. Her eyes go like this. So it's really pretty impressive. So a lot of things in nature, we really need logarithms to describe. And when, like my example of the raise, hey, I got a 10% raise. Wow, that's really good. I don't care whether you work at Starbucks or whether you're George Clooney, 10% raise, pretty good thing. $1 an hour raise really doesn't mean a lot without the context of where you are. I'm defining the log domain with that. So that's my sales pitch for dB. So what I want to do now is look at different plots that we use for frequency response. Now, you saw that frequency response is a complex value. Why is it complex? Because we got a j omega here, we got a j omega here. And so frequency response at a given frequency has some magnitude and it has some phase. So it's a complex value. So here I go. How do you show a complex value? Well, for frequency response, we're just going to use two plots. And the first plot is the magnitude of the frequency response. Here it is, 20 times the base 10 log of the magnitude of the transfer function. And you see here, it's a function of omega. It's a function of omega. You'll also see it as a function of frequency. Don't forget the 2 pi, that's not good. But in this case, we're showing it as a function of omega. What kind of filter do we have here? We have a low-pass filter, just like our RC filter. So this plot is in dB, and it's showing us the magnitude response. This plot is this plot, right? And I could have written dB right here because we can see, well, I could have written dB right here. That's how you typically look at frequency response. But frequency response is complex. So we also care about the phase. So we're going to make a separate plot for this transfer function, meaning that to describe a transfer function, I need 2 plots. And here is phase, here is frequency. And you notice, of course, on both of these plots, frequency is shown with the exponent linearly increasing, meaning that we're showing the log of the frequency. And for our RC circuit that we did in the last example, you'll see that it has no phase shift at 0, and it has minus 90 degrees of phase shift at infinite frequency. So those are the 2 plots. And here they are. Our transfer function is 1 over 1 plus j omega RC. And I'm going to split that up so I can make these 2 plots. So what I'm going to do is use the Pythagorean theorem to get my magnitude phase, and then I'm going to use just an arctangent, I'm sorry, to get my magnitude here, and then I'm going to use an arctangent to get the phase. Now, this is a really dumb thing, but it really confused me when I took this class years ago. I would say, hey, wait a minute, Pythagorean theorem is root of x squared plus y squared. Why doesn't that j squared give me a -1, and why isn't this a -1 right here? That drove me nuts, but just like you, I was trying to hang on by my fingernails in the program, so I never really got a good answer. But remember, we're not using the Pythagorean theorem. For the Pythagorean theorem, we're just trying to get the magnitude of the hypotenuse. Think of this as a real value. This is a complex value. This is an imaginary value. We just want to know how big the response is, the hypotenuse is. So we're going to take the real part, the imaginary part. Forget the j. Just give me the value of the hypotenuse. And that's why this ends up being positive. Silly little thing, but it used to bug me. Doesn't bug me anymore. Okay, so now let's do an example of frequency response that's a bit more involved than our last one. And so we have a circuit here. Here's our input. Here's our output. We want to find and plot the frequency response. I'm going to triage this thing with asymptotic analysis. So far, I don't have a transfer function, but I'm going to just do it for the circuit. At DC, I know that I have no voltage across the inductor. So the magnitude of j omega is going to be 0. If I was in dB here, it would be -infinity. So we're not in dB right here. So we're going to put our 0 right here. Now I'm going to look at the response at infinity. Now at infinity, my inductor is going to be an open circuit, but 1 over j omega c with omega is infinity is going to give me 0 impedance here. So I have another 0. So at DC, the inductor made the frequency response 0. At infinite, the capacitor made the frequency response 0. What's the response in the middle? I don't care, but it's somewhere up here because it's an absolute value, right? So I got a 0, I got a 0, and I got a something in here. So that's what asymptotic analysis tells me. So now let's get the transfer function. So what do I see? I see a voltage divider that is made out of this clump and this component. So here's one effective component, here's the other. So V out over V in is equal to ZL in parallel with ZC divided by ZL in parallel with ZC plus R. It's just a voltage divider, but I'm calling this clump ZL in parallel with ZC. Now I'm going to show you another simple little trick that just makes life easier for me. Some students look at this trick and think it's really cool and use the heck out of it. Other students look at it and say, God, Professor Dorr is lame to need simple things like this. So you pick whether it helps you, but it really helps me. So here's my expression. And you know I don't want to go to numbers until I need to. So I like this as a good start. But now I'm going to say, what's ZL in parallel with ZC? Well, it's going to be SL times 1 over SC divided by SL plus 1 over LC. So let's multiply through by SC, and I end up with SL here. Now I get an S squared LC plus 1. Here's the deal, though. I'm going to just call this N over D, because it's a simple fraction, and it's got a numerator, and it's got a denominator. So I'm just going to call it N over D. And I know it's kind of a star in this formula here, right? So now my V out over V in becomes N over D divided by N over D plus R. And I can immediately see that if I multiply through by D, I'm going to just get N over N plus dr. See how I'm doing things simply and I'm not getting ground down in all the numbers? It's just N over N plus dr. So let's take N and stick it right here. That's SL. And then N, which is SL, plus D, here's D, times R. So I kind of just saved myself a step. So I see this on a lot of student exams and finals, and it's always nice to see you guys using this. Other students don't, that's all cool. So, but now I'm ready to start multiplying things out. And as always, I'm in no hurry to do any numbers. So H of S looks like the hole punch kind of took my H. V out over V in. Let's just multiply this out, and I get SL divided by S squared RLC. Looks like that's that piece, plus R plus SL. And we'll work through a little more here. We'll divide top and bottom by RLC. You say, why are you doing that? And the reason I am is because it's customary to have this S squared with a coefficient of 1, because there's a lot of design material for these kinds of networks. And so everybody's kind of agreed on the S squared term being 1. So I just kind of naturally do it like, you know, red and yellow dogs like to chase tennis balls. So I divide through, and then I look at what I end up with, and I got my 1 over RC times S over S squared plus S over RC plus 1 over LC. Now you look at this and you say, hey, look at the similarity between this and the parallel RLC characteristic equation. It uses S, right? And this is that characteristic equation. Let's go back and look at the circuit. I got a capacitor up at the top of my circuit. I've got, and the capacitor goes down to ground, which is a low impedance point. I've got an inductor that goes down to a low impedance point. I've got a 50 ohm resistor that goes to a low impedance point. Remember, the Thevenin resistance of this input source is 0. So, of course, these are in parallel. Now, you may not get that all the way right now, but you will when you get into 330 and we talk about AC grounds. So always good to think about them now. And this is just a real good example of one. And I also like pointing this out because EE310 is just full of trap doors between all the materials. I spent 35 years in industry finding all those trap doors. And I'm not going to lay every single one of them on you because you're just trying to get through the class. But this one is pretty cool because it goes right back to the characteristic equation. It's using the same S that we used in Chapter 8 for thuds and boings, and it's using the same S that we're going to use in Laplace transform. So all this stuff is connected together. But let's get back to what we're doing. We went through asymptotic analysis and we said we got nothing at DC, we got nothing at infinity, and we got something in the middle. So now let's look at our transfer function. So at DC, S is equal to 0. That means I got 0 divided by 0, 0, something. So I got 0 divided by something. That gives me 0. Bing, that agrees with my, my circuit. Now let's take the frequency to infinity. And I got an infinity here, And I got an infinity squared here, but I only got a regular infinity here, and I got nothing here. So I really have infinity over infinity squared. That's 0. So notice that my 0 from my transfer function agrees with my 0 from the circuit. My infinity from the transfer function agrees with my infinity from the circuit. And I have no idea what's going on here, but since this is an absolute value, I know it's not 0. It's not negative, so it's somewhere, something like this. And I tend to just call it something. All right, so now I want to leave that for a bit, and I want to go back to this whole logarithmic business with the Kardashians' money and Phil Rivers' money. Man, we're going to miss him in San Diego. But I want to work with that a little more. Here's my problem. I want to create a set of frequency values that are uniformly spaced on a log plot. So let's go up here. I've got a log plot here, and I've got frequency. Now, here's 1 Hertz, or 1 radian per second. Got me 10 to the 0, and here's 10 radians per second. If I want any detail in my plot, I should probably show what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 Hertz, so maybe 10 points. And they'll bunch up a little over here, but that's okay. But now I'm going from 100 Hertz to 1,000 Hertz. Do I want to space my points out by 1 Hertz? No, because I'm going to have 900 of them, and I don't need 900 points to represent this transfer function. I'd be fine with 10 points. What if I'm up here at the Koch brothers' money? Am I going to be spacing my points by $1? No, because my graph will be too complicated. So if I'm doing a magnitude response or a phase response, what I really want to do is say, you know, I'd like, let's say, 10 points per tick here. That way, I'm going to have 10 nice little uniformly spaced frequency points between each of my divisions. Well, I'm not going to get that incrementing by a certain amount, like I can't go 10, 20, 30, or 40, or whatever. I got to increment the log by a certain amount, because that's what's linear on this plot. The log is going up linearly. So let's learn a new way to count. My problem is that I want to create a set of frequency values that are uniformly spaced on a log plot. I'm going to start at frequency fs. That's frequency f start. Because I got to start somewhere other than 0, because I'm on a log plot, and I can't represent 0 on a log plot. So we're going to start at frequency fs. And then I'm going to say, how much should I plot? And we'll say, let's cover d decades. Each one of these is a decade, right? 10 to the 0, 10 times that is 10 to the 1. 100 times that is 10 to the 2. So each of these is a decade. So what I'm saying is I want d points per decade. So that's part of my problem setup. Sorry, I want d decades total for my plot, and I want points per decade, ppd, points for each decade. So here's how I'm going to specify what I want my plot to look like. So what I know is my plot is going to contain the number of decades times the number of points per decade points. And here are the frequencies. This is the important thing. F of k is equal to f start times 10 to the k over points per decade. And k is going to go from 0 to the number of points, d times ppd, minus 1. So you can see that what's going up linearly is my exponent. So this is going to give me a nice uniform set of points on a log plot. So let's say we're going to start at a megahertz. We're going to display 4 decades. 1, 2, 3, 4 decades. And I'm going to plot 200 points per decade. And what I can do is say when k is greater than points per decade, I'm just kind of giving you some sanity here. When k is greater than the number of points per decade, I have f start times 10 to the points per decade plus some value, right? Because we're greater than points per decade, which I can say is equal to fs times points per decade divided by points per decade. Hello, that's 10, so we'll put it down here, times k prime, which is the additional here, points per decade. So all this makes good sense. So I can't do this lecture without giving you another cool example of this. So what I'm going to do is go to one of my favorite things, which is music, and let's go to a piano keyboard. So on the piano keyboard, we've got 12 tones for an octave, right? We'll start at middle C, C, C sharp, D, D sharp, E, F, F sharp, blah, blah, blah. There are 12 tones, and when we get to that 12th tone, we're back at C again. It's called an octave. And instead of working in decades, which are factors of 10, our sense of pitch goes by octaves, which are factors of 2. So if I double the frequency, that's an octave higher. Ba, ba. I'm not going to try to sing the next octave. But instead of a factor of 10, I'm a factor of 2. So what I can do is say that the frequency of any note, let's do a C scale just for fun. The frequency of any note in the tempered scale is equal to the start frequency, which is like 235 Hertz or something for middle C, times 2 to the D over 12, where D is the tone. It goes from 0 to 11, or 12 if you want. And that gives you the note of every piano key. We're working in octaves. I'm going to give it to you one more time because some of you guys really dig this and you actually work with it. F of D, where D is the index of the note, is equal to the start frequency times start frequency times 2 to the D over 12. That is the nominal frequency of all those keys on your piano keyboard. So it's really a pretty cool thing. All right, let's move on. Let's take this transfer function right here, and let's plot the frequency response using Matlab. So we're going to go to my little compute frequency response function, which I've posted on Blackboard. If you're not in my class, if you're somewhere out there on the internet, my email address is bdorr, B-D-O-R-R, at sdsu.edu. And chances are I'll just send you a copy of it, especially if you bought my book. No, I'm just kidding. So let's look at some Matlab, since I know some of you are new to it. So the percent symbol, that's how we show comments in Matlab. And Matlab is an interpreted function, not a compiled function. So we want to clear the workspace and clear out any plots that we have. Otherwise, we won't always get the same behavior every time we run it. So clear and close, I believe, have been replaced with just clear vars, but that's a detail. Let's do our logarithmic counting that we just talked about. Our start frequency is 100K. That's our lowest frequency to plot. The number of decades is going to be 4. The number of points per decade is going to be 200. So I'm going to get 200 nice, evenly spaced points on my plot. Now I'm going to pre-allocate the results matrices. I'm going to get a magnitude, a phase for each frequency. So I'm going to make 3 matrices. One is going to be the frequency. The next one's going to be the phase at each frequency. The next one's going to be the magnitude at each frequency. And these frequencies, I tell Matlab, just define a matrix and put zeros in it with this many rows and that many columns. You don't have to use these statements, but Matlab will bitch at you and say that the size of the array is increasing on every iteration and therefore it'll take longer to run, but it runs this so fast, doesn't really matter. So the values for the example are R is 50, L is 82 nanohenries, and C is 26.5 picofarads. So I kind of get my numbers out of the way up here. Now what I'm going to do is go through a loop where what I'm going to do is I'm going to say increment this index I from 1 to the number of points we have, which is number of decades times the points per decade. For each index, I'm going to determine the exact frequency. It's equal to my start frequency times 10 raised to the I over points per decade. Namely, this formula. So that gives me the frequency at this iteration. Now I'm going to just say S equals J times 2 pi F. So now I have S nailed down, and what you see is from here, I can enter my transfer function directly. This is exactly what we calculated for our transfer function. And then I'm going to say the magnitude is equal to the absolute value of that, duh. The phase response, I put it in degrees by saying it's the angle of H, which comes back in radians because smart people all like radians. And I divide my radians by 2 pi, which gives me the percentage around the circle it is, and then I multiply that by 360 degrees. And then I place those in these matrices that I allocated up here. Now I'm going to plot the magnitude and phase. And one of the best things about Matlab is that it has incredible plotting features. They're not super easy to use, but once you get it, you get it. And it's pretty cool. Let's actually go over to Matlab. And here's my script. And let's run it. Run. And look at those beautiful plots. So let's take a look at what we've got here. You can see I'm working in Hertz. Sometimes you work in radians, sometimes you work in Hertz. Get used to that. Here's my magnitude response. Here's my phase response. Let's see. So we said that our frequency response was going to look something like this. We're going to have 0, 0, and something. Let's look. I ended up with, it's on its way down to 0, and you'll learn more about that in the next lecture. And it's aiming towards 0 up here at 10 to the 10th. And it's something in the middle, 10 to the 8th Hertz. So it has its maximum frequency response right near 10 to the 8th Hertz. 10 to the 8th Hertz, that's like 100 megahertz. Looks kind of like this, doesn't it? That peak is 100 megahertz. let's go back to my plot. Actually, let's go back to our filter first. Here's our little bandpass filter. Here's the frequency response. Did we make the filter that we needed for that airplane to receive the VOR station but reject KGB FM? Well, no. The reason we didn't is our filter doesn't have enough what we call selectivity. In other words, we made a filter that peaked at 108 megahertz. That's great, but the trouble is at 101 megahertz, it's pretty much going to let that pass through. And what you're going to learn in the next few lectures is if you want to make your filter more selective, you got to add more components. And smart people have figured out exactly the ratio and the topology of those components that will give you as steep as a filter or as selective of a filter as you want. So we'll see that more as we get into Bode plots. Okay, so that is our introduction to frequency response. In the next two lectures, I'm going to show you how to do Bode plots, but I'm also going to show you at least my take on where Bode plots are still relevant in 2020 versus where they're irrelevant. You'll have some people out in industry who say, oh, Bode plots, we don't need those anymore. You know, we have tools for that now. I don't agree with that. And there are people who say, well, it's absolutely important that you know how to do a Bode plot of any circuit. I don't really agree with that either. But for me, there's a sweet spot where Bode plots have just been really, really useful for me. So I hope to see you in those next two lectures. As always, I look forward to seeing all my students at office hour. So I will see you then.